Hello. So now make sure, yes. Okay. Making sure everything's in order here. All right. Now it's on to section 2.1, where we're going to talk about the derivative. Okay. So let's define some things here. Let's say let a function f map the reals onto the reals, a real valued function. Okay. Let k be any real number, an element of the real numbers in the domain of f. We say f prime of k is the value of the derivative of f evaluated at some x is equal to k. Really what that means is if this is our function, let's see here. If this is our function f of x right here in the red, this is our function, let's say this is f of x. Okay, then we can say that the derivative of the function at some point k, let's say this is some k right here. This value right here is going to be f of k, all right? Then f prime of k is literally the value of the slope of the tangent line at that point k. Boom. Okay? It's the value of this slope for this tangent line at that point k. So right here, whatever this slope is for this tangent line in the blue, then that is what f prime of k is equal to. Namely, f prime of k is defined to be f of k plus alpha minus f of k all over alpha. This should be familiar to you because this is very much what the slope was, a generalized slope. So f prime of k is the slope of the function, is the slope of the tangent line to the function at the value x equals k. All right. So we say that if f prime of k is equal to some L or some M, whatever, it doesn't matter. We say that that is the derivative of f at k. Okay. Let's do some examples. What about our function f of x is equal to x squared? What is f prime of 5, for example? Well, by definition, f prime of 5 should equal f of 5 plus alpha minus f of 5 all over alpha. By definition, this is f plus alpha squared minus, 5 plus alpha squared minus 5 squared all over alpha. This becomes 25 plus 10 alpha plus alpha squared minus 25 all over alpha. 25's cancel. We can factor out an alpha, so we get alpha plus 10 all over alpha. Cancel out the alphas, you get alpha plus 10, which renders the real result 10. So this is what our f prime of 5 is equal to, or our f of x is equal to x squared. Okay? Let's do another example. All right. Let's do f of x is equal to 5x plus 1, for example. So we wish to find what is the derivative of the function at 3. Well, f prime of 3 is equal to f of 3 plus alpha minus f of 3 all over alpha. This is the same thing as 5 times the quantity 3 plus alpha plus 1, parentheses, minus 5 times the quantity 3 plus 1, all over alpha. So this ends up being 15 plus 5 alpha plus 1 minus, and we'll put parentheses, 15 plus 1, all over alpha. 15 plus 1 is a 16. These two combine to become a 16. So notice this becomes 16 plus 5 alpha minus 16 all over alpha. 16's cancel. We get 5 alpha over alpha. Alpha's cancel. So we get 5. This is equal to our f prime of 3. Okay. Okay. Again, going back to what is the graphical interpretation of what we're talking about? Well, let's say you have f of x is equal to x squared. This is x squared. Our function f of x is equal to x squared, one of our favorite functions in mathematics, the parabola. Okay. When we discovered that f prime of 5 was equal to 10, what that implies is that here at 1, 2, 3, 4, 5, here we have a f of 5, which is 25, because that's what 5 squared is. We say that the slope of the tangent line at that point right here, the slope of the tangent line at this point right here, by our calculations, let's make it a true tangent line. There we go. According to our calculations, the slope of this line in blue has value 10. So the slope of this line, m, is equal to a positive 10. And that makes sense because the line has a positive slope, as you can see. So clearly it has value, a positive value, and our calculations reveal that its value is positive 10. Okay, so that's what that means. So can we construct, what is this tangent line t of x? Can we construct what this equals? It should equal some mx plus b, right? But what is it equal to? Let's discover that. We know what the slope is. M is equal to 10. We also know a point, some x1, y1 on that graph. It's 5, 25, which is 5, f of 5, which is equal to 25. Okay, so then we can use slope, or point slope form. Y minus y1 is equal to m times the quantity x minus x1. That implies we have y minus r25 is equal to the slope 10 times the quantity x minus 5. So this becomes 10x minus 50. So that implies we get y is equal to 10x minus 50 plus a 25, which is equal to 10x minus a 25, which is equal to our y, okay? And to honor our notation where I wrote t to represent tangent, this means our t of x, a function of x, is equal to 10x minus 25. Okay, so that means over here, the y-intercept is a minus 25. Clearly, I have not drawn the tangent line to scale, okay? But if I had drawn it perfectly, the y-intercept would be negative 25. It has slope 10. There you go. That's where all this stuff becomes useful, because now, given a function, we can construct the tangent line to any point of that function that we desire. We just calculate the derivative, the value of the derivative at that point, tells us what the slope of that tangent line is. And then we know the point and we know the slope of the tangent line. We can construct the equation for the line. Now, what if f of x is equal to x squared represented the motion of some particle or the motion of some object? Well, what would the derivative imply? Well, if f of x equaled position, then f prime of 5 would be the instantaneous rate of change at time equals 5. Because that's how fast it's changing at time equals 5. So it would be changing at 10 units per second. So keep that in mind, that if our functions represent positions, then we take the derivative of them, then they represent velocities. So derivative of a position function gives you instantaneous velocity. Don't forget that. That's very important. Matter of fact, Gottfried von Leibniz and Sir Isaac Newton invented calculus to be able to calculate these things about physical objects in motion. So this whole discipline was created for this purpose. So Isaac Newton wanted to calculate what are the orbits of the planets, and it required the invention of calculus for it. Very cool. So now notice, let's say our f of x is equal to some x squared again. We don't have to just compute f prime of 5, which we know is 10. We can compute f prime of x in general. What is it as a general function? Then when we find what the general function is, then we can plug in any value at that point, and we can discover for any value here, what is the slope of that tangent line? For any value here, what is the slope of that tangent line? It would be merely the same thing as plugging a value into a function and seeing what it equals after you do the arithmetic. So f prime of x in general will equal f of x plus alpha minus f of x all over alpha. Notice this equals x plus alpha quantity squared minus x squared all over alpha. Notice this equals x squared plus 2x alpha plus alpha squared minus x squared all over alpha. Cancel out the x squares, factor out an alpha, you get alpha plus 2x all over alpha. Alpha's cancel, so you get alpha plus 2x, which renders the real result 2x, which is equal to our f prime of x. This is the general derivative of the function at any input. So notice that f prime of 5 would then equal 2 times 5, which restores our value 10, just like in our calculation above. But now we don't only know it at 5, we can figure out f prime of negative pi. Notice that that equals 2 times the negative pi, so it's negative 2 pi. We know f prime of negative 100. That's 2 times negative 100, which is negative 200. So we can figure out what is the instantaneous rate of change at any input. We can figure out what is the slope of the tangent line at any input, which is very cool. It's very useful in real life as well as just being purely mathematically interesting. It has quite a bit of real life applications. It would be very difficult for you to find any form of technology that we utilize in today's day and age that isn't based off of calculus. There is not a single piece of technology that we use in today's day and age that does not have the undertones of calculus in it. Mostly because technology is really just applied physics. Applied physics is engineering. Engineering is just applied physics. And so physics is just applied mathematics. And applied mathematics is just math. So everything goes back to math, guys. Every single thing. Without mathematics, none of the things we have that make us distinct from all the other animals on this planet would be possible. Okay? So let's do another example. What about f of x is equal to x cubed? What is f prime of -1? Well, we could just find what is f prime of x and then plug in a -1 when we finish. So f prime of x is the same thing as f of x plus alpha minus f of x all over alpha. This is the same thing as x plus alpha quantity cubed minus x cubed all over alpha. This ends up equaling x plus alpha times x squared plus 2x alpha plus alpha squared minus x cubed all over alpha. This ends up equaling x cubed plus 2x squared alpha plus x alpha squared plus alpha x squared plus 2x alpha squared plus alpha cubed minus x cubed all over alpha. X cubes cancel. Let's see what we get here. Now we get an alpha cubed. Go away. What about the alpha squared terms? We have a x alpha squared and a 2x alpha squared, which gives us a 3x alpha squared. And what about the alpha x squared terms? We have an alpha x squared and a 2 alpha x squared. So this gives us a 3 alpha x squared. All over alpha, we can factor out an alpha. So we get alpha squared plus 3x alpha plus 3x squared all over alpha. Cancel the alpha out. So then we get alpha squared plus 3x alpha plus 3x squared. Okay. Notice that this renders the real result 3x squared. This is our f prime of x. So then if we want to know what is f prime of -1, that's just merely 3 times the quantity -1 squared. That's just 3 times 1, and that's 3. We can figure out what is f prime of 2. That's just 3 times 2 squared. That's just 3 times 4. That's 12. Okay? So we can ask, what is the slope of the tangent line of f of x is equal to x cubed at x is equal to 4? Well, that's just f prime of 4, guys, which is just 3 times 4 squared, which is just 3 times 16, which is equal to, oh, this one is hard. 32 plus a 16, that's a 48. All right. I believe that's enough examples of doing that. Now let's talk about how does differentiability interact with continuity? Okay, let's have some examples here. Let's have a vertical asymptote here, and then let's have a function that behaves like this. Here's our function f of x in red. Okay. F of x is discontinuous at x equals k. Would you guys agree? It has a plus infinity discontinuity. Now, is the function differentiable at x equals k? Meaning, does f prime of k exist Well, f prime of k would equal f of k plus alpha minus f of k all over alpha. Notice that f of k is undefined. F of k is undefined. Technically, it would be undefined, but if you got, yeah, f of k is undefined, all right? So that implies f prime of k is equal to, you could say that f of k plus alpha is, you know, positive infinity. Let's say capital A, minus an undefined all over alpha. This is undefined. So that implies the derivative does not exist. Okay? So if you're not continuous, it seems like you can't be differentiable. Now, if you're, let's see what the two give us. We want to compare and contrast what does continuity imply about differentiability, and what does differentiability imply about continuity. Here we have a function that is discontinuous here, but it's also not differentiable here. So could we conject that discontinuity at some point implies non-differentiability? It seems like that is so based off of the definition of the derivative of the function at k, because whenever you utilize the derivative definition, this component is undefined. So we can't compute this algebraic expression with an undefined quantity. So the derivative doesn't exist. Let's continue to peruse some more examples here. What about a type of function like so? Let's say we got something like this going on here. This is our function f of x in red. Clearly, the function is discontinuous at f of k, at x equals k, because f of k does not exist. It's undefined. Now, this is a removable discontinuity because we could define f of k to equal the limit as x approaches k, which then would equal whatever that limit value is. But if we don't do that, based off of what we're just purely given, f prime of k does not exist as well, for the same reason as the previous one. F of k is undefined, therefore we can't algebraically have an expression that quantifies the derivative value. So if the function is undefined at x equals k, it seems like it's discontinuous and it's not differentiable. Now, let's talk about something different here. Let's talk about an example like this. Let's talk about this function in red. Okay. This function, is it continuous? It has a jump discontinuity. So it's not continuous. Is it differentiable? Well, to be differentiable, if let's say this is k, f prime of k has to exist, but that's equal to f of k plus alpha minus f of k all over alpha. F of k exists, okay? F of k is defined. So is the function differentiable at this point? We're not running into that problem as before. This is actually defined now, so it's okay. But what about this right here? Notice that this is technically not defined. Why? Well, when alpha is a negative number, that value pops down here. When alpha is a positive number, that value pops up here. So if it was up here, then f prime is 0 because these would be the same. And when the numerator is 0, their overall fraction is 0. So alpha positive implies f prime of k is equal to f of k minus f of k all over alpha, which is equal to 0. But alpha less than 0 implies f prime of k is equal to this value down here. We could call this f of k plus, and we can call this f of k minus, for instance. This becomes f of k minus f of k all over alpha, and this does not equal 0. So what happens here is that between these 2 points, the slope of the tangent line would have to be infinite. And I know what you're thinking. Hey, this reminds me of the bonus question on the last test. Well, it's very much like that because you would have a vertical line, a vertical tangent line. So this function is not differentiable. But that doesn't mean it's not continuous, okay? It does have a jump discontinuity. So it isn't continuous. I'm not saying it is continuous. But you can have a continuous function that is not differentiable. Here's an example. Here's a continuous function that is not differentiable. Let's say that this is in red, f of x is equal to the absolute value of x plus 1 as a vertical shift of 1. Notice this point right here is a corner. It's a corner point. What does a corner point mean? Well, notice that this function is defined as a piecewise defined function. It's supposed to equal x plus 1 if x is x plus 1. And you want to know what? How about I not make a example that would be hard for you to follow? Let's just use absolute value of x, so it's a little less stuff to keep track of for you. All right. This is absolute value of x. It's defined as a piecewise defined function. It equals x when x has values greater than or equal to 0. But it equals negative x otherwise for values of x that are less than 0. Notice that it is a continuous function because the limit as x approaches 0 of absolute value of x is equal to absolute value of 0 plus alpha, which is equal to the absolute value of alpha. Okay, which in both cases, whether it's positive or negative, equals 0, which is the same thing as absolute value of 0, which is evaluating the function at 0. So whenever you evaluate the function and it outputs the same as take the limit, that means it's continuous. So the absolute value of x is continuous, but it is not differentiable at this point. So it's continuous, but not differentiable. Why? Well, f prime of 0 is defined as f of alpha plus 0 minus f of alpha all over alpha. Okay. Notice that that's equal to absolute value of alpha minus absolute value of alpha all over alpha. Okay. Let's bring this calculation to another page. So f prime of 0 is the derivative of absolute value at 0. That's the same thing as alpha plus 0 minus alpha all over alpha. So this ends up becoming alpha minus alpha, absolute value of alpha minus absolute value of alpha all over alpha, which you could say is, oh, that's 0 over alpha. That should equal 0, right? So the derivative should exist, right? Not so fast. Notice that alpha is an arbitrary infinitesimal number. So it's either positive or negative. So case 1, positive case. Then we get this. Okay. Case number 2. Then you get this. Notice that this becomes negative alpha plus an alpha all over alpha. All right. But then again, this equals 0 over alpha, which equals 0. So what's going on? In both cases, it equals 0. So should it not be differentiable? It seems like a derivative exists. It seems like f prime of 0 exists and f prime of 0 is equal to 0. But that is not true. Okay? And here's why. Over here, when I said alpha is less than 0, and when we did this trick here, we also have to put a negative on this alpha. And we also have to put a negative on this alpha. So we also have to put a negative on this alpha. So notice that the difference now becomes this, which renders the real result 0 here and renders the real result 0 here. But notice that there's a difference here and here. And you can visually see that from the absolute value function. Notice that the slope of the tangent line a little to the left of 0 will be this, -1. The slope of the tangent line is equal to -1. But a little to the right of 0, the slope of the tangent line is equal to +1. Okay? These two slopes have to agree for the left side and the right side. Okay? So these two slopes have to agree. And since they do not agree, the derivative does not exist. Another way to see that is to say, well, f prime of 0, when we did this calculation here, is to see here and here. We notice that, of course, there's no +0 or there's no -0. But as you can see that the absolute value of x is defined to equal x if x is a positive or 0 number, and -x if x is less than 0. So over here, we could have written alpha is greater than or equal to 0, and we would have gotten this. And over here, we could have written alpha is less than 0, okay? But notice that, what about alpha equaling 0 here in this case. So case 1 can break apart to case 1a. What about alpha is equal to 0? Of course, alpha shouldn't equal 0, but what if it did? Well, then you get 0 over 0 over here in this calculation. You get 0 over alpha is equal to 0 over 0, which is undefined. So, yes, in the case when alpha is greater than or equal to 0, you get 0. In the case when alpha is less than equal, which is less than 0, you get 0. But what about when alpha is actually equal to 0, a value that it can actually have? We get an undefined quantity. So the derivative in general cannot exist because we want to know what is f prime at 0. So at 0, this funny business is occurring. And it's a consequence of this geometrical interpretation of the absolute value function. A little to the left, the slope is -1. A little to the right, the slope is +1. You can also see this from the limit idea. The limit as x approaches 0 of the absolute value of x. What is this? Well, the limit as x approaches 0 from the right of absolute value of x is equal to absolute value of omega, all right, which is just omega. But that the limit as x approaches 0 from the left of absolute value of x is equal to the absolute value of negative omega, which is equal to negative absolute value of negative omega, which equals omega. Both of them render the real result 0. Okay. So this shows that the function is continuous because absolute value of 0, which is equal to 0, is equal to the limit as x approaches 0 of absolute value of x. It's continuous, but it's not differentiable because when we examine the derivative, we have the case where we have an undefined quantity. The derivative should be defined for all possibilities. Okay, so what is the lesson here? The lesson here is that differentiable, if you have a function that is differentiable, that implies you have a function that is continuous. However, if you have a function that is continuous, as in the case of absolute value of x, it's a continuous function, that does not in general mean that it's differentiable. In general, you cannot assume a continuous function is differentiable at all points, but you can assume that a differentiable function is continuous at all points. So now let's talk about the local linearity formula. This states, here's a theorem, that f of k plus alpha is approximately f prime of k alpha plus f of k. What does this mean? It means, well, given a function As crazy as it is, you know what? That's not a crazy enough function. Let's create a really crazy function. There you go. Let's forget this one. We want it really crazy. Given a very crazy function like this, all right, let's create a little window. Let's create a little window right here. Let's expand that window out here. Let's zoom in. Once we zoom into that point, we have the fact that the function is actually doing this. Okay. And then if we zoom in again at some point like this, zoom in again up here. That at that point, if you zoom in far enough, the function looks like this. And then zoom in again right here. And then the function looks like a straight line. So what this means is, even in the craziest of functions, if it is continuous and differentiable, that what you get here is you can zoom in so far that it becomes a straight line, even at the craziest points. All right. Now I know what you're thinking. Why can't you zoom in enough on the absolute value function and do this? Well, the way I drew this is not so great because it looks like it's a corner. Assume that that is not really a corner. In the absolute value function, it is indeed a sharp corner. But over here, it's different than the absolute value function, okay? So I wish I drew that a little bit better, but that's what's going on. It's saying that a continuous function, whenever you zoom into it, really, in essence, it is a straight line at any point, okay? And this makes sense, you know, like think about us on the surface of the planet Earth. Everything looks flat to us, but when you zoom out, you notice that we're on the surface of a sphere. That's called local linearity in 2 dimensions, okay? That's what local linearity in 2 dimensions is. It says that curved functions, when you zoom in enough, they seem flat. That at some point, you can approximate it as a flat entity. Even though globally, when you zoom out, it's not flat, it's curved. So let's talk about functions that are differentiable everywhere. These are called smooth functions. Are functions that are differentiable anywhere. For example, f of x is equal to x squared is a smooth function. Why? Well, f prime of x we calculated is equal to 2x. That means its derivative exists for any input, any real input. Its derivative exists. You want to know what is derivative at x equals negative 5,000? That's 2 times negative 5,000. That's negative 10,000. So we can figure it out at any point. So a smooth function is differentiable everywhere. So this function is a smooth function. All right. Smooth function also means it has no corners. So absolute value of x is not a smooth function. Okay. The value at x equals 0 messes it up. Okay. For example, let's try and find what is f of x is equal to the cube root of x. What is f prime of 0 equal to? Well, f prime of 0 is the same thing as f of 0 plus alpha minus f of 0 all over alpha. That's the same thing as the cube root of alpha minus the cube root of 0 all over alpha. This is the same thing as the cube root of alpha all over alpha. This is the same thing as alpha to the 1/3 power all over alpha. This is the same thing as alpha to the 1/3 power times alpha to the -1 power. This is the same thing as alpha to the 1/3 power minus 1. This is the same thing as alpha to the 1/3 power minus 3 all over 3. And this is the same thing as alpha to the 1 minus 3 all over 3 power, which is the same thing as alpha to the -2/3 power, which is the same thing as 1 over the cube root of alpha squared. Okay. Now, when we render the real result, what do we get? We notice that alpha to the -2/3 is the same thing as 1 over alpha to the 2/3, which is the same thing as 1 over alpha to the 2/3 power. So notice that's the same thing as capital A to the 2/3 power. Okay. So this is the same thing as the cube root of capital A squared. Now, capital A could be positive infinity or negative infinity, but when we square it, it always assumes a real positive value. So we know that this is going to actually render the real result positive infinity. So what does that mean? Well, let's graph the cube root function. Let's graph the function cube root of x. Cube root of x looks like this. This is the cube root of x. And so at x equals 0, you notice that there's this infinite tangent line. All right. So this is called a tangent line of infinite slope. So that's why you're getting this value. The slope is actually infinity because it's going up vertically. Why? Well, m is equal to y2 minus y1 all over x2 minus x1. In this case, if right here, this is our x1, y1, and over here, this is our x2, y2, notice that x1 is equal to x2 right here. All right. Even though y1 and y2 are not the same, x1 and x2 are the same. So that means over here we got y2 minus y1 all over x1 minus x1, which is equal to y2 minus y1 all over 0. This is why we get this infinity, because you're dividing by 0, technically. That's why it has infinite slope. So you need to be able to analyze non-differentiability. So here's first case. F continuous at x equals k implies I think this should say if f is not continuous at x equals k, that means f is not differentiable. Okay. So if f has a corner That implies f is not differentiable. And if f has a vertical tangent, again, that implies the same thing. So non-differentiability, you have to look out for discontinuities, corners, and vertical tangents.